Audible? Fantastic. So, morning everyone. You're all having fun at OPLSS, I hope. I've just got here. I've been trying to catch up with everything you've done so far. I gather it's been a lot of theory, a lot of whiteboard. I'm not going to do that to you. I'm going to do sort of the programming equivalent of a whiteboard lecture, which is I'm going to do some coding. I'm going to do some live coding. So what I'm going to do before we start is I've got lots of pieces of paper here. Has everyone brought a pen? Because you're all, programming language people, so you know that pencil and paper is the way we do things. Yeah. So I'm going to send a notepad around and just ask everyone to take a not necessarily a whole piece of paper, but just a scrap of paper, because I'm going to ask you to do something later on. Don't worry, it's not homework or anything. So, right. So, hello. My name's Edwin. I've come all the way from Scotland to tell you about dependent types in the Idris programming language, and I'll say a little thing about Scotland. So, Scotland, as I'm sure you know, is the home of functional programming. And we now fly the flag like this because Haskell came from Scotland and ML originated in Scotland, and there's quite a lot of programming language researchers currently in Scotland. I think a lot of people in the community have spent a lot of time in Scotland, and it's only fair that the country recognises that this heritage. So, my contribution to Scottish programming languages is the Idris programming language. So Idris is going to put into practice quite a few of the things you've been looking at over the last few days. So I like to describe it as a Pac-Man complete functional programming language. So people talk of Turing Completeness, and I reckon Turing Completeness is kind of overrated because what does Turing Completeness give you? Well, you can certainly solve all the computable problems. And all kinds of surprising things turn out to be Turing complete. So, if you want to solve an interesting problem in C++ templates, you can, because they're Turing complete. If you want to solve an interesting problem in, I don't know, send mail configuration files are apparently Turing complete. PostScript's Turing complete. But you wouldn't write Pac-Man in any of these languages. They're not really geared up for whitespace is Turing complete, for goodness sake. None of these things are geared up for writing actual practical software, stuff that interacts with the outside world. So I like to say Idris is Pac-Man complete. It is, by the way, Turing complete, but that's kind of incidental to the whole thing. So a challenge for someone, by the way. I've not proved that Idris is Pac-Man complete. I have done Space Invaders, and I have this sort of hypothesis that Space Invaders completeness implies Pac-Man completeness. So, if any of you are looking for a PhD topic still, that's just putting that out there as a possibility. So, has everyone successfully got Idris installed? Because if you do have Idris installed, I've put a few code samples out there. There's going to be more. If you follow this link, tinyurl.com/idris-oplss. I've also written it on the board there. If you follow that link, you'll find a page with links to these slides, links to some example code that I'm going to be working through. And if you have it installed, you can kind of sing along with the lectures. And if you want to try something different, if you want to see what happens, please do that. Please tell me how it goes. So, just to say, this is my plan. This might change. I mean, we've got four days of lectures here. I'm certainly open to feedback about what you want to hear about. So the outline or the plan as it currently stands, I'll tell you a little bit about just what Idris is all about and what I like to call type-driven development. I particularly like the name type-driven development because it abbreviates to TDD, and that's what TDD should stand for these days. There's a lot in common with test-driven development in that it's kind of about decide what you want to do before you do it, but that's kind of where the similarity ends. So today I'm going to be talking about what I mean by type-driven development and some of the fundamentals of the language. So we'll spend quite a while doing some small programs and just working towards interesting programs with dependent types. And because if we spend a lot of time on that, then the interesting stuff later on becomes easier to follow. So I also want to talk a bit about total functional programming. So the benefits of knowing that your programs will always terminate, or knowing that your server will keep producing results. So I'll say a little bit tomorrow about how to achieve that, and what the benefits are. And I gather you've, I think Bob set you an interesting problem the other day of doing GCD in System T. Did anyone try that? Did anyone succeed? It is quite comical, the solution, if you see it. So we'll talk a little bit about how to achieve that in maybe slightly less comical ways, and maybe what the limits are of that kind of approach. And then after you've had a day off on Sunday to recover, we'll talk about some more kind of putting Idris into practice. So talking about domain-specific languages, dealing with stateful systems. So dealing with the outside world essentially. So that's the plan at the minute. It might change. You should ask me questions, and if you want to see something else, or if you want some variation on this. And this is actually crucial. So I want to sort of emphasize this. People probably said this several times so far, but I want to say it again because it's really important. If there's anything you don't get, please ask me things. Anything you want me to explain again or better or differently, please ask me things. So there's a trick to this actually. I know, particularly because these lectures are being videoed. I know this sometimes means people kind of are reluctant to ask questions. There's a trick to this, which is if you think your question is going to be silly, nudge the person next to you and ask them the question. And if they don't know the answer, then there's at least 2 of you in the room who don't know the answer. And at that point, by induction, it's worth asking the question. So please do that. Also, I'm going to say now the reason I've given you this piece of paper. So with this piece of paper, I want everyone, at the end of the lecture, and you can think about it as the lecture goes, I want everyone to write their name, what they got out of the lecture, and a question that you want to ask me. And what I'll do is, later today, I'll go through these, and at the beginning of tomorrow's lecture, I'll just try to summarize what people have asked, and maybe it'll direct the way things go. And as an extra special incentive, I'm doing some shameless promotion. I have brought 1 copy of this, so this is Type-Driven Development with Idris, and I also have 2 codes for an ebook version. And what I'm going to do is take the pieces of paper and do a draw at the beginning of the 2nd, 3rd, and 4th lecture, and whoever I draw out will win one of them. So that's incentive to ask me questions. So I'll try to figure out some way to make it fair. And yeah, well, yes, whatever. There's some kind of theory. Yeah, anyway. You can also ask me things on Slack. You can come and find me afterwards if you don't want to ask them publicly. So there's all of these. You should make use of all of these methods of asking me questions. I'll be around for a few days. Take advantage of that. So, why types? I guess you've had a lot about why types and what are types. I'm going to tell you why what types are about for me. So, when you first encounter statically typed languages, whatever it happens to be, you might sort of see the types as being a thing that is there to sort of tell you off when you did it wrong. So you spend ages hacking your work of art, and you feed it to the compiler, and pretty much guaranteed the compiler says, no, you've done it wrong. This is, none out of 10, see me after class. That's not really a good way to view, I don't think that is a good way to view types. So types are there not so much for checking that a program does what you want it to, checking that a program has the intended properties, rather to help you get towards the correct program. So you shouldn't see the type system as being like your teacher telling you you've made a mistake, you've done it wrong, you failed your homework. You should see the types as being like your research assistant. So by putting the type first, you're saying to the machine, this is what we're going to work on together. So it's very much an interactive process. It's a dialogue with the machine, and at the end of the dialogue, you have a program that hopefully does what you want. There's going to be a lot of back and forth with this. When you write down the type first, you don't necessarily have the type right. In fact, you almost certainly don't have the type right. So there's kind of a process you get into of write the type, define the function, then refine the type and function as necessary. And it's I sort of got this 3-word. I was told when I was writing this book that you somehow by law you have to have a 3-word soundbite that you have to say if you're coming up with a development methodology. So test-driven development has red, green, refactor. Well, type-driven development we say type, define, refine. And I resisted this for a long time until eventually I just I've said it so much that I actually think it works kind of well. So you think about the type, you come up with your initial model for what the problem is. So I mean, in a sense, that's what types are. It's like a model for thinking, for your model of what's going on in the world that you're trying to implement. And that is going to develop a little bit as your understanding of a problem changes, as you understand more about the problem. So as you start defining functions, you'll refine your idea of what that type is, and it just is this cycle that keeps going until you ship it. So just think about this as we go through. Write the type, define the function, refine the type and the function as your understanding develops. So just to briefly go through, this is like a bird's eye view of Idris. And just actually, by way of show of hands, who doesn't know Haskell? Okay, that is quite a few of you. So that means that I'll explain a little bit more some of the features that relate to Haskell. So of those who raised your hands, do you read Haskell? Could you look at a Haskell program and say, yeah, I kind of know what's going on there? So there's a little bit of maybe. Okay, so please do say if I go too fast, if I forget to explain something, I'll try to remember to explain all of the syntactic details. But if I forget, please do wave and I'll make sure to do that. Just to summarize the sort of bird's eye view of what Idris is all about, what we have is I like to call them first-class types. So when you're first introduced to functional programming, sometimes people talk about functions being first-class things in the language. So that meaning that you can assign functions to variables, you can pass them to functions, you can return them from functions. Essentially, you can treat them like any other construct in the language. With a dependently typed language, types become first-class constructs in that you can assign types to variables, you can pass types to functions, you can return types from functions, so you can compute types. So that's really all there is to it. It's as simple as that. Types are first-class. There's a type-level language, there's a term-level language. They're the same thing. So it's a compile language. It targets C by default, so it's a fairly cheap hack backend, to be honest, but it targets C and it works okay. It's also a JavaScript backend. It's retargetable. There are other things, other languages you can target. But crucially, it takes type erasure very seriously. So you tend to find when you're working with fancier and fancier type systems that you end up with bits of program that you never have any intention of executing. They're only there to show that the program works, essentially, to show that the types match up. So we have to go to some lengths to make sure that everything that isn't used gets erased. So that is, I think, a distinguishing feature of Idris compared to other similar languages. So we work quite hard to compile things well. And I think this is something that there's a lot of open problems here. So we like to say that if you are precise about what the program is going to do, so if you give very detailed types, that really should give the compiler a lot more information to work with when building the program, when generating the machine code. So in theory, very precisely typed programs, dependently typed programs, should be a lot faster than simply typed programs. In practice, that's not the case. That's because there's a lot of work still to do. But maybe you're going to be the people who do it. And if you're interested in that, again, please talk to me. Probably one of the bigger differences with Haskell is Idris has interfaces rather than type classes. They're superficially exactly the same thing, but there are some slight differences. So the differences like in Haskell, if you have an instance of a type class, then you know that all of the instances of that type class are the same. So there's this coherence property that if you've got one instance of a type class, it's the same as the other. So if you've got one instance of a type class for some type, then they're all the same. That's not true of Idris interfaces. You can have lots of different implementations of an interface for the same type. So it's kind of more like ML modules, if you've encountered ML modules. So strict evaluation rather than lazy. Half the room thinks that's brilliant and half the room thinks that's terrible, I suspect. Yeah, okay. So let's not have that discussion. It just is what it is. So you can have lazy evaluation if you need it. So lazy evaluation is by type. So there's a lazy type that says essentially delay this until later. We'll see a little bit of that later on. And there's a little bit of foreign functions, system interaction, and in the last lecture we'll see a little bit of this. So it's really, at the end of the day, this is a programming language. You can do all sorts of cool type stuff. You can prove things about your programs if you like, but at the end of the day, it's about writing programs that interact with the outside world and trying to get them right. So there's a bit of system interaction, foreign functions, and so on. Okay, so, oh yes, I do, the kind folks at Manning have given a special discount code just for this meeting. So you can look that up later. So I promise there's not so much more shameless promotion to come, but this is something they want me to do. So. Okay, so let's go on with some hacking. So finally, after a few days, if you have your laptop open, you can try to play along, and let's see how it goes. So I have an atom buffer set up. So there are interactive editing modes for, off the top of my head, Emacs, Vim, Atom. I think VS Code has one. I mostly use Atom because it's not my text editor of choice, but I find that if I use either Emacs or Vim, half the room think because I've picked one, that means the other's not allowed. I don't quite get how this works with text editors, that somehow you have to pick one. So what I've done is I've picked neither of the two text editors in the world, and that way everybody hates me or something. I don't know. So I'm using Atom. One advantage of Atom actually is the key, the shortcuts are relatively familiar. So for any other piece of software, so it's kind of the neutral choice. So and there is an Idris interaction mode that you can find it if you haven't installed it. You can find it on. Where can you find it? Preferences, packages, and then search for it. So I won't show you the details of how to do that now, but you can, I guess you can figure it. There we are, language Idris. So it is easy to install the extension. Basically, is what I'm saying. Right. So we're going to start with just a demonstration of what I mean by types being first class. The idea being that because types are first class, you can write functions which compute types. And because you can compute types, well, where do you use types? You use types in type signatures. So we can generate interesting types of functions by computation. So the first one I'm going to do is just a function which, given a Boolean, returns a type. And if that Boolean is true, the type is string. If it's false, the type is, it's going to be nat. So nat is the type of natural numbers, so 0 upwards. So the positive integers and 0. And it's unbounded. So, and just a note on the syntax. If you know Haskell, there are two differences in syntax. One is that the type here, this is the argument type. You're allowed to give that a name, and I find this nice for documentation purposes, but it will turn out to be crucial later on. So I just like it for documentation purposes here. So we've got, if you don't know Haskell, the syntax is, you'll have seen this in lectures so far. Function type is A arrow B. That's how we write it down. Function type is A arrow B. But we can give names to the argument type. The other difference with Haskell, this still trips me up actually when I switch between Idris and Haskell, is that there is only one colon for the type signature, and we made that choice because that's correct. So I say that sort of thing because I know these things are getting videoed, and there'll probably be a link on Reddit at some point, and this is, hi Reddit. Hi Reddit. I'm going to resign from the internet now. It's just, I'm going to have to. Right, good. So, everyone okay with that syntax? Question, yes?
So do you not need to start your files with modules like you do with Haskell? Is that
So you don't, the question, do you need to put a module declaration? Do you need to start the file with module? No, you don't. You can, so I could put module stuff. If you don't do that, then it's assumed to be called main. So also notice that I haven't put any definitions for these functions, and it's okay with that. So if I load this up in a REPL, so let's So Idris generally, interaction with Idris is either through your editor or through your read eval print loop. So both are useful things to have up and running. So I normally, because my resolution is normally a bit better than this, I normally have them side by side and both visible, but I'll just have the one visible here. So I call that intro 0 TDD. So that green is not visible at all, is it? So I'll turn color off. Color, by the way, is spelt like that. Okay. You can spell it without a U if you really want to, but I'm just on principle going to do that. So what you see if you load this file up, is you see it reports the holes. So holes are bits of a program you haven't written yet. So this is where the interactive side starts to come in. You can present Idris a program that isn't complete yet, and by talking to the machine back and forth, it will help you get to the program that you actually want to run. So if I try compiling this, and nothing's going to happen. In fact, I think I haven't got a main. Okay, so clearly nothing is going to happen. So it complains if there are holes that are undefined. It will quite happily, as long as you have a main function, it will quite happily run that program. But if it gets to the hole, at that point it will say encounter the hole. So it's like, So you can develop programs, you can compile them as you go, and just get the machine to help you as you're developing it. Right. So let's actually write this function, this very small function, string or nat. And what I'll do is hovering over the name string or nat, I'll hit Control-Alt-A. So A is short for add definition. So the way to remember the key shortcut is to remember the name of the command. So add definition A. It's almost easier just to remember the command, I suppose. But anyway. So what it does when you say add definition is it adds this skeleton definition of the function. So like Haskell, like other pure functional languages, you define functions by essentially recursively defined equations. So I'm giving a left-hand side and a right-hand side, and well, that left-hand side will evaluate to the right-hand side. So this is a familiar thing to everyone. If it's not, please ask now. No. So that is sorry. How did I add it? So I hit Control-Alt-A with the cursor over the function name. So this thing on the right-hand side here, this is another hole. So it's standing for a bit of the function that is not yet complete. So what I can do is if the cursor is over this hole name. So this is a valid Idris program, valid syntax. And it says to the machine, I don't know what goes here, but it's a hole, and you can give me information about the hole. So hovering over this hole, I can hit Control-Alt-T, T for type, and it will tell me about that hole. So in this window at the bottom, it tells me that I have a thing in scope called isstr. I'll pronounce it isstring. So I have a thing in scope called isstring that's a type bool, and I need to give back a type. Okay? So what I was going to do was say if it's false, then so string or nat, isstring is false, then I want to give a nat. If it's true, then I'll give a string. So the way to do this is hovering over isstring, hit Control-Alt-C, C for case split, and it will give you the two possibilities for that thing, and then we'll finish it off just by filling in the right-hand side. So that was going to be nat, and then this was going to be string. So there we are, first Idris function. And we can go to the REPL. And what I like to do when I've written functions is I like to test them, because we run our programs. This is sometimes controversial in world of dependent types, because people say things like, it type checks, ship it. Or they say things like, why do I need to run my program? I already know it works. And, well, okay, that's kind of funny. But people say this without actually qualifying it with, actually, you do need to test your programs, because how they interact with people is important. Whether you're writing even the right program is important. And sometimes your types aren't actually so precise that you know you're doing exactly the right thing. So types are there as they're a great way to help you get to the right program. They're a great way to help you work through what you're doing to get to the right program, but it doesn't stop the need for testing. And there is no dichotomy between types and testing, no matter what people on the internet say. Just because you have types doesn't mean you can't add more tests, and you should add more tests. So I want to make this really clear right up front. I'm absolutely not saying that types replace tests. Good. Clear on that.
Can I ask you a quick question?
Yeah, sure.
So then, if you get to the point where you think you might have something that's ready to go, is there a directive you can give to ask the compiler to check to make sure that you haven't left any holes or that you haven't?
Okay, so yeah. So the question is, I don't know if everyone heard the question. I'll repeat it. The question is there a directive you can give to the machine when you think you've finished to get the machine to say there are some holes left? So there's no directive, but it will always tell you. If you try to compile a program and there are holes in it, it will tell you. It's not necessarily an error, and maybe there should be a flag that turns that into an error, so thank you for the feature suggestion. But there isn't at the moment. Yeah, another question.
So then what happens when it tries to execute a piece of code that has a hole?
So I'll show you that a bit later on. So it's, I mean, it will essentially crash, but it'll tell you exactly why it crashed. But I'll probably show you an example of that in a bit. Right, so let's move on to why we would even do something like this, because this sort of feels like a little bit of trivia so far, but it's absolutely crucial what we've just done. So if you have a function that calculates a type, I mean, where are you going to use a type? You're going to use a type as part of a bigger type. And this is where the idea of dependent types comes in. So we talk about dependent types. When we say dependent types, we're really meaning that there are types which can depend on, be computed by, be predicated on. So types which are computed by some other values. So types which can be computed. So if we have this function string or nat, that means we can use it as part of another type. So this function here, length or double, it's going to take, again, an argument is string, which is a Boolean. And then the second argument, the type of this second argument is going to be different depending on what the value of the first argument was. So let's just see how that works. So again, I'll do Control-Alt-A to add a definition. And it's good form, I find, to whenever the system presents you with a new hole, it's good to look at that hole and see what its type is. So it tells us that we have something called isstr of type bool. We have something called x of type string or nat isstr. And well, how are we going to proceed? The idea of this function is if it's a string, I'm going to give you its length, and if it's a nat, I'm going to double it. And I don't know what x is yet. So the only way I can find out what x is if I look at isstring. So what I'll do, therefore, is again put the cursor over isstring. Control-Alt-C to do a case split. And, okay, system's given us two new holes. Good practice. When you get a hole, look at the type of that hole. So if we look at length or double RHS1, we'll see that it's refined the type of x, because it now knows that isstring Boolean was false. So it knows a bit more about what x is going to be. So it's now definitely a nat. So I can write the function as if it's a nat. So it's going to be x plus x. And then in this case, surprise, surprise, check the type. It says x. Oh, x in this case is a string. So, yes, question?
Could you just mention what are the control sequences you're using, like check the type you use?
So when I'm over a name, I can hit Control-Alt-T, and yes, I've already done it. So I hit Control-Alt-T over the name, and it gives whatever information it has. So if I do it over length or double, for example, then it'll present it in a slightly different way. It'll say this is a definition with this is a function with this type. So there's
scrolling up quick, we're still getting something set up while you do the first function.
oh right, yes.
So just wanted to, okay, thanks.
Okay. So. So by the way, I get the impression that people are just following along, which is fantastic. At some point shortly, I'm going to speed up a little bit. And so what's going to happen is you're not going to be able to keep up, but you've got the code. So when it comes to the hands-on sessions, your job is to basically reproduce what I did or didn't have time to do. So you take these types as your questions, and you can figure out the answers during the sessions, and you can ask me if you want to know a bit more about how to proceed. Right, so we've got length or double, and we'll just see that in action. I'll go back to the REPL. I'll need to reload. So if I say length or double of false, and I just happen to have forgotten what the type of this is, and it says, oh, that's a function from nat to nat. Length or double true is a function from string to nat. Okay, this making sense? This is a thing that you don't typically expect to see in a simply typed programming language, that you give an argument and suddenly the type of the function has changed. But this is what happens here. So length or let's do length or double of false. I needed to give a nat, so let's give it 47. Okay, and if I give that true and 47, it's not happy because string or nat true is not a numeric type. Well, that's true. Okay. So why would we write functions like this? This again, I mean, it still seems like a kind of weird, esoteric thing to want to do. But anyone done any C programming? Yeah, that's most of you. So you've seen printf, right? So formatted output given some argument string. That argument string tells you what the type of the rest of the function is. So what we've just done is exactly the sort of thing you're doing when you're writing a function like printf. It's just that printf, it's the dependently typed function that C compilers have. Hooray! C has dependent types in a few very different ways. One is printf, tends to be hard coded into the compiler. I guess another one is size of. It's kind of an example of a dependent type in C, but it has to be hard coded into the compiler. Here we can build it up from first principles. So given that we can do printf, we might as well. So I might as well show you how that works. So I've completed printf. I'm not going to go all the way through this. So this is something to look at. If you want to see how this works, look at it sort of outside the lectures. But just to show you that this concept of computing types stretches to something like printf. So I define the possible formats, and eventually, when we get down to the bottom, we've got a printf type which says f is a format string, and we're going to compute the type of the function from that format string. So a little bit more complicated than that string or nat thing we've just seen, but exactly the same principles. And just to try it out, so if I check the type of printf %s%d, that's a function takes a string and an int, gives back a string. Or if I add a few more things, then it's just making the function type longer. So, yeah.
How does your printf deal with strings that are not known till runtime?
That is an excellent question. So the question was, how does printf deal with a string that's not known till runtime? It's an excellent question with a very long, hard answer, I'm afraid. So what you have to do, I'll only summarize this, and hopefully by the time we get to the end, it'll be a bit more obvious what's going on. If you don't know something until runtime, you basically now have no choice but to write some kind of checker that makes sure that what's given at runtime is valid for the rest of the input. So if you have, let's imagine you're writing a web application. The web application takes some input from a user, and maybe that input from the user, maybe it's a form, for example, so there's some various fields on the form, and maybe there's a function to process that form, which is calculated from what's in the form. Yeah? See what I'm getting at? So that is going to be some function constructed from the input data. That's exactly the situation you're talking about, stuff that arrives at runtime that you don't know about. Now, would you take any old input from a user on a web form and just deal with it? I don't think you would. I think you would verify it first. You would validate it first. So what happens here is you're in a position where the type checker says, I don't think you validated that input. I think you need to do something to check that user has given you the right data. So essentially you have to check it. Techniques for doing that are not immediately obvious. We'll see some as we go. Maybe at the end of this lecture we'll see a first instance of how that works, and then we'll build it up. But that's a really good question, just because the answer's not easy. Okay. So that's computing types. That's one side of dependently typed programming. And to introduce the next bit, so I want to talk a bit about data types. And I'm going to do this with a program that most of you will have seen before. It's not going to have any dependent types, at least not obviously visibly, just to see where things get better when you add dependent types. So we're going to write the append function on lists, and I've written as a comment here, this is how the list data type is defined. So just like Haskell, you define data types by giving the possible ways of constructing that data type. If you haven't seen Haskell, just to say the syntax here is that we're introducing a list data type. It has a parameter called a. If you don't say anything about that parameter, then Idris will assume that that parameter is a type variable. And we give the possible constructor. So it's either nil or it's a cons, and cons takes the element and the rest of the list, so the head and the tail. So this is a linked list data type. So hopefully nothing too surprising there. If there is anything surprising, please ask, of course. We'll go through the same process, write a type, come up with a definition, refine the definition until we've got a program that works. So because append is defined, or these functions here are defined in the library, I've just renamed them my append. So just as before, if we hit Control-Alt-A, we'll get an initial candidate definition for that function. Notice it's come up with names X's and Y's because that's what we call lists. So there is a way of telling the system what the name of variables should be by default. And just like before, we can use Control-Alt-C on a variable to do a case split on that variable, give us the possible values for that variable. So if you're defining append, we'll do this by looking at the first argument, and then, we'll start by looking at the first argument. And one thing that I should note here, just this square brackets, this is slightly strange when you first see it because I called it nil earlier. This is a bit of syntactic sugar. So rather than writing lists in full as a Slack comment, hello, I thought I turned that off. Well, everyone now knows there's a way to ask me questions without speaking. Let's just load that up. So if I should turn the color off. So I can write a list in this form, cons of 0 or cons of 3 of nil, and it will give you the form in the syntactic sugar. So I can rather than writing lists in full in this rather verbose syntax, I can write it in this form just as comma separated elements in brackets. So the reason it's that's just a long way of saying the reason it's given us empty brackets rather than nil is syntactic sugar. So to append y's onto the empty list, well, the first list is empty, so the result must be y's. And to append xcons x's to y's, well, we can make a recursive call, so we can let's do this bit by bit. I can leave holes as I'm writing definitions, and I find this is good practice actually. As you're writing more complex expressions, it's good practice to just build it up a bit at a time, so that the machine can tell you a bit more about what the types of the sub-expressions need to be. So I can check the type of first, and it says, yeah, first is going to be something of type A, and then rest is going to be something of type list A. So just fill that in. Okay, so if you're writing so your ordinary function on an ordinary polymorphic, generic data type like list, you can do that by pattern matching, like in Haskell. This would work in Haskell if you swap the double and single colons around, so reasonably conventional there. Okay. There is something slightly unfortunate about this, though, which is that I could write something complete. I could write some complete nonsense, and it would still be. It would still accept this. So this wouldn't be a very good append function, because like the length of the result is wrong, and like the value is going to be wrong. So if I'm a little bit more precise about, if I had a bit more precision into what I'm saying to the machine, if I refine my idea of what this type is going to be, then the machine is going to be able to give me a bit more help. So instead, I'll leave these as exercises for you. So if you've done functional programming before, then these will just be a kind of warm-up to get your fingers used to the interactive editing. So I'll leave them for you to do later on. So if we then add a little bit more information to the type, not only is that going to give us more confidence that the program we write is going to do the right thing, so the machine is going to reject programs like I've just done, where I've written the empty list instead of wise. Not only that, the machine is going to tell us more about what we need when we're writing that function. So, this is the canonical introductory dependent data type. Therefore, I have to do it by law. So this is the vectors. Vectors are lists that are indexed by their length. So that the type of a list, so that list 1, 2, 3 has length 3, so the number 3 is going to be in its type. So the way to do this is I'll show you the definition of NAT from the prelude, NAT from the library. So NAT has actually defined itself as an inductive data type. So NAT is either, we had a conversation about this in the pub last night. This is pronounced Z. Sorry, you're all going to hate that. It's going to drive you crazy, but I am going to pronounce it Z. I also, you know the beardy rock band from Texas? ZZ Top. I can't help it. I'm sorry. Right. So NAT is either Z, or it's the successor of another NAT. It's like unary numbers, basically. You add one more thing. So doing this is clearly a terrible idea for runtime performance, but it's really nice that you have this inductive structure of natural numbers, because that inductive structure is also the structure of, say, lists, or maybe the height of trees. And this comes up an awful lot. Also, by the way, we don't really compile it this way. The compiler knows about natural numbers being defined as 0 and successor, and it will say, you know what, I'm going to compile that as a GMP integer, as an arbitrary size integer. So it's not completely crazy. But it's nice to define them this way, because it just gives you that structure, that corresponding structure. So when we define vectors, vectors are lists with length. So when we define that data type, it's slightly more complicated than defining lists, because each of the constructors, so nil and cons, rather than, well, they don't both have the same type. So they both have a type that's kind of built up inductively with the data type definition. So nil, the empty vector, that has type vect 0. Maybe I'll say 0 instead of Z. Maybe that'll be less irritating. So I'll pronounce Z 0. So vect 0 A. So nil is empty. The type says so. So rather than giving it in this Haskell style of presenting the constructors and their type arguments, what I'm doing is I'm giving the type of the type constructor. So vect itself has a type. It takes a natural number length. It takes a parameter type, and it gives us back a type. Nil, that is a data constructor. It has a type. And nil takes no arguments, and it gives us back an empty vector of element type A. And then cons, given some element A, and given some vector with k things in it, that gives us back a vector with successor of k things in it, because we've just added one. So
Where
yeah.
is A bound? Like, do you
Right, where is A bound? Also, where is k bound? So any this is a convention that we followed in the language. So is that any name that begins with a lowercase letter that you write in a type is implicitly bound. And the reason for this is that it would be really annoying to have to write in full A is a type and K is a nat, because at that point, while you're programming, cons suddenly has 4 arguments, and nil suddenly has 1 argument. And this gets very noisy. So when it comes to writing these programs, the machine, if I write 1, 2, 3 as a vector, then the machine can already tell that the length is 3, because it's like inductively built up from that vector. And it can already tell that the element type is integer. So it takes an integer as the default if you give numeric literals. So the machine can figure that out by unification, so it does so. So if you think the machine can figure something out on its own, then you can just write it as a lowercase name and it will implicitly bind it. Yeah, another question.
Can you explicitly declare an implicit argument?
Yep, you can. So can you explicitly declare an implicit argument? Yes, you can, just like I did, but I put it in braces rather than So that is allowed. Sometimes it's a good idea. It actually does have implications on how erasure works as well. So we might see a little bit more about that later on. So the idea is, so the starting point for erasure analysis is if you write it in the program, it's assumed that you want it at runtime. If you don't write it, it's assumed that you don't. That's not necessarily how it always works out, because sometimes you write stuff down that isn't needed. So the machine will sometimes erase more than you think, which I consider a good thing. Okay, so let's do what we did. Yeah, this %name, if you're wondering, is just a directive to the machine, to the interactive system, that when it comes up with a new thing, that's where you get the names from. So every time it sees a vector, it'll call it x's, then y's, then z's in that order. So let's define append just as before. So slight difference with the type is that as well as the element type, which stays the same throughout, the first argument has a length, the second argument has a length, and the result has the sum of the lengths. So just start as before, Control-Alt-A, we get the candidate definition. Is that loaded? Yes, it has. There was a slight pause while it reloaded. If I do a case split on x, well, okay, let's do the same thing. If we get a hole, look at the type of the hole. Just good practice. Shouldn't be too surprising here. Well, it's maybe slightly surprising. Rather than saying n plus m, it's noticed that we're talking about nat as a natural number, and plus is overloaded via the interface mechanism. So there's lots of implementations of plus for all the numeric data types, and this thing that's explicitly called plus just happens to be the function that defines it for nat. So that's why this expansion here. But otherwise you see the types that you expect from the type signature. You'll see explicitly that it's worked out what the types of A, M, and N are. So these are just things that the machine has to know about before it can make progress. So we'll see that we have A is a type, M is a nat, Y has length M, X has length N. So as before, we'll do a case split on X's. And the interesting thing here is if we look at the type of the right-hand side, we'll see that, so because it now knows a bit more about this vector, it knows that this vector has nothing in it. It knows that it's length 0. So it knows that the result type we're looking for is 0 plus m, which reduces to m. So the definition of plus on natural numbers, just to show you up here, 0 plus y gives you y. So it's happily reducing to m there. And so if I try that thing that we did before of giving the empty vector, this will hopefully not work. So this is to prove that sometimes there are type errors and it is really doing something and I'm not cheating. So it says, unfortunately I can't make this font any bigger, so unless someone's done something to the atom mode since I last looked. So if anybody fancies adding a feature to the atom mode where I can make this font bigger, that would be lovely. Thank you very much. It says type mismatch between 0 and m. It was expecting something of length m. It's got something of length 0. So rather than trying to write that program ourselves, given that this compiler seems to know something about this program, what we could do instead is just say S, Control-Alt-S for search. And, well, the only thing it could be is Y's. So let's put it in. So let's do the same for the second case. So we've got... So just check the type of the hole, see what we've got. Okay, so X is of type A, Y's is a vector with M things in it, X's is a vector with K things in it, and somehow we need to come up with a vector of K plus M things and one more. Any guesses how we might do that? Well, it's told us, well, we've got a thing, the X is our thing, we've got a vector of length K, we've got a vector of length M, and so there is a natural way of putting these together, which is the element at the beginning, then a recursive call. Did you get that, Idris? Yes, it was listening. So I hit Control-Alt-S there, and because it knew a bit about the structure of the program, and because also I had this slightly fortunate coincidence between the structure of the plus function and the structure of append. Yeah, some people are nodding like, yeah, see, you're cheating there. So because there's this fortunate coincidence between the structure of things, the machine can tell us more about the program. Yeah, question?
Can you do a repeat n plus n x?
Repeat. Yeah. So basically, can I construct a vector that is? Can I construct something that's not the append function, but is still type correct? And the answer is yes. There are plenty of incorrect implementations of this function that don't do vector append that would nevertheless type check, which is, it's fine as far as the type system is concerned, but there's a trade-off going on here. So you can give more precision to your type so that you can only write append. So like the only type correct thing really will be append. But the thing is, what have you gained by doing that? You've gained the ability to write the append function perfectly. Now let's write reverse. Hang on, a bit harder. So there's always this trade-off with how to define your types. What do you put in the type? What level of precision do you put in the types? What do you index them over? And I don't have a general answer to that. It's actually quite hard to figure out what it is. And my approach is typically to start with the least dependent thing possible. So in this case, it would be lists. I mean, it's not because I just happen to have written this function probably more than 1,000 times now. No, probably not that many. It's certainly in the tens and maybe into the hundreds. So I happen to have written this a lot. So I know what the right way of indexing this thing is. But as you're working on a new problem, you've got to figure that out. And this is where the whole idea of type define refine comes in. You come up with your initial idea for what the type is supposed to be. You try writing the function, and at some point you might hit a point where you can't implement the function, or there's a case for the function that doesn't quite make sense. And that's the point where you start thinking, okay, a little bit more detail in the type here would help me, and you do a bit of refactoring of the type level program. So that's always a tricky thing to think about. How precise should the type be? And it's a matter of understanding the problem over time and refining your idea, the model of the problem that you have in your head. Right. So let's do one more because there's questions. Yes.
Is there anything that indicates? Does it ever tell you that I'm just guessing here or here? I know it's the only thing that it can be.
Yeah, that's a very good question too. So the question is there anything that indicates how confident the machine is of its answer? Is that another way of putting your question? Yeah. So no, there isn't. And I have to, at this point, admit that this really is a cheap hack. What it does is looks at the type and brute force tries literally everything it can see until it works or it gives up. So if it doesn't work, typically you'll just see it'll just increment the number on the whole. It might give you a partial solution. Quite often it'll give you a wrong solution, and there's really no substitute. Even though this is here to help the machine to have the machine help you do like bits of plumbing that are kind of tricky to figure out. So those of you who have done Haskell programming, like imagine you're writing, I don't know, monad transformer stack or something. If you can bear to imagine that. And there's always some bit where you have to do some really awkward plumbing, but the types tell you what the plumbing is, but the machine's saying like, I know how to do this, but I'm not telling you. Well, this is for situations where the machine can help you out to get you to the right program. So it's not really, this whole expression search thing, it's not really a substitute for knowing the function you want to write. It's a good idea to look at what comes out and see if it is really what you expected. And by the way, this is another thing that would be great for people to work on, to have better ways of doing that proof search, having better interaction. So this really is an interactive editing thing. It's almost an HCI problem. What is the right interface for the programmer to talk to the human, even in a language like this that is essentially, in the end, text-based? What is the right interface for the editor? Is there a way of presenting, say, multiple solutions and being able to browse through them? So if anyone's played, anyone play with Agda? A few of you. So you might have seen AGSI. So AGSI is a more sophisticated tool that does, I think it presents more possible answers to the problem, more possible programs. So there's sort of interface questions there of, how does that interaction work? At the minute, I find it works quite nicely just for, quick searches for things where there can only be one answer, but there's really no guarantee that it is the only answer. Yeah, question? AGSI, A-G-S-Y. So I think it's actually, someone might correct me if I'm wrong here. I think it's implemented separately from Agda. So some nodding. So David thinks, yeah. So maybe it's possible to plug AGSI into Idris. That would be a fun. It's more an engineering project than a research project, but it'd be quite fun to have. Everyone else? Anything else anyone wants to ask? So is this making sense? Some nodding. Okay. Let's do another one. Why not? Let's do zip. So you know the zip function. So the zip function is a function that takes two lists and, well, zips them together. So imagine, you know, on your jacket, you zip up your jacket. You've got a list of things. You've got another list of things, and it's basically putting a comma between them. So it's joining them up. So it's called zip because that's what you do on your jacket. So if you had a jacket where one side of the zip was the different length from the other side, it would be a bit of a strange jacket, wouldn't it? So this is a strange thing to do with zip. Well, it's not necessarily a strange thing to do with zip, but generally when you're zipping two lists together, you want the two things to be the same length, and if they're different lengths, you want to have some sensible thought about what to do when they're different lengths. You don't want to be surprised about if you're making the assumption that the lists are the same length. It's nice to be able to express that assumption. So what we're going to do here is exactly that: express that assumption. And by the way, this is one way to think about dependent types, is to say, right, I am making assumptions about my program. And if I'm writing in a more simply typed language or a polymorphic type language, I might write those assumptions as comments. And the thing about comments is that you change your program, but you don't change the comments. Yeah, don't try to convince me otherwise. 6 months later, you violated that assumption, but the machine isn't telling you. So this is like a way of making those assumptions explicit and having the machine tell you if you do a bit of refactoring that violates that assumption. So was that a question? Yeah. Global variables that are bound somewhere else? Do you mean? I mean, you can define top-level functions that just have a constant form, but global variables that you can mutate, no, you can't do that. Oh, right. Right, so the question is, therefore, if I happen to define n, if I do that, what happens? And so what happens is, the rule is, if the name begins with a lowercase letter in a type, it is always implicitly bound. And that's exactly to stop this kind of thing. So this is actually, we've had quite a lot of discussion about this. This is quite a tricky trade-off, because somehow you want to be able to write types in this nice, concise, readable way, but you also want to avoid this kind of problem, that which n does it mean? So in the unlikely event that I really do mean the globally bound n, I have to be explicit by, what did I call this module? This is called main. So this thing has a full name, main.n. And if I really mean that one, I have to explicitly say that I really mean that one. So it is. This is actually something that you occasionally. Well, I occasionally trip up over this, where I put a name in a type. It's a constant. It's a global thing, and I forget that it's a global thing. And the only thing that's going to happen is I get a type error. So it's not going to go badly wrong for me because I've written a type that's too general. But it's certainly something you have to watch out for. So yes, thank you for bringing that up. There are all kinds of questions about what the syntax should be here. Should it be a completely separate syntax for type level variables? Maybe it should, but it's not. So, so there you go. Yeah, another question. No. I mean, if you want to have some kind of way of saying there's a parameter here, maybe. No, you can't do that. So it's just a syntactic choice, really. If you're familiar with this distinction between parameters and indices, then I'll say then Idris will try to figure out which ones you mean to be parameters. If you're not familiar with the distinction, don't worry. I might explain it later if we get time. But you can always ask me about it if you want to know. This is one of the decisions of taking Idris as a programming language rather than a theorem prover, is that this is the sort of thing that it's kind of important internally, but not something that I feel needs to be presented to the programmer. So no, you can't do that. Yeah.
Sorry if this question is falling behind somehow, but I was trying to use the band function here.
Mm-hmm.
And
So the vector one.
Yes, and I didn't have to specify the length of my vector, so I assume it's implicit, right?
Yeah.
Why did you say that on our definition? How does Idris know that
So if you write vector ABC, for example, so that's going to be cons of A, cons of B, cons of C onto nil, okay? So nil, if you look at the type of nil, it's 0. Or the length of nil, it's 0 in the type. If you look at the type of cons C of nil, that's going to be successor of 0 in the type. So if you look at the type, there is only one thing it could possibly be. So what the machine does is it sees that you've left that argument implicit. So it leaves internally, it leaves a hole for that. And just while it's type checking, it will generate some constraints and it will figure out the solution to that constraint problem. So, and the solution to the constraint problem here is it's always going to find the length if you give an explicit vector. So
if I want, where
let me yeah. So I'll show you how to do that because this is a thing that's worth knowing. So what you did was you did presumably append 1, 2, 3, 4, 5, 6, something like this, and it's come out with that's a vector of length 6. Okay, so you've got 1, 2, 3. That's your vector n. So I can give an explicit value for the implicit argument by saying something like this. So n has length 3. Yeah, and it's happy with that. Now, what I could do, I suppose, is I could give something wrong for n and see what it does. Maybe I won't give it something that big. So it says, mismatch between 0 and 1. That's slightly strange, actually. You might think mismatch between 3 and 4. The reason it's mismatched between 0 and 1 is what it's done is it's gone all the way down the successors, right to the point it hits 0 for one and successor for the other. So you can give implicit arguments you can give explicitly. Sometimes that's a useful thing to do if it's only for documentation purposes or matching purposes, and sometimes it's maybe not. Okay, so time is marching on, and I'd like to do zip, and then I want to just do quickly a bigger example of vectors, and I think it's probably a good time to stop. So I'll just work through that, and unless there's anything else anyone wants to ask about what we've seen. No? Okay, good. Because this sort of thing that people are asking is going to come up, so it's great that you're asking these things. So we'll do zip. So the thing about zip that we didn't see with append is that we've made this assumption explicit in the type that things are of length n. So I'll go through the same process of case splitting on x's. And now if we look at this hole, so it's generated a couple of holes, zip RHS1, zip RHS2. Check the type of zip RHS1. And we see this interesting thing about y's, which is that the machine is now convinced that y's is empty. Well, it has to be, because x is empty. We've explicitly said in the type that the things are the same length. So if I were to do a case split on y's, it's only going to give me the one possibility. It can't possibly be cons, so it's only given me that one possibility. And again, I'll just do search for the right-hand side. Similarly, for this second case, if I do a case split on y, well, let's look at the type of the hole first. It knows what it knows about y's is it doesn't know its length exactly, but it at least knows that it's one more than the length of x's. It's got to be a successor. So that means basically it can't be nil. So if I do a case split on y's, it's giving me the only possibility, which is it must be of the form y cons y's. And again, if I do a search here, there's only one reasonable thing it could be. So it's going to tell me what that is. Okay, so that's how we would take two vectors and zip the two of them together. And I guess we could test it because we like running our programs. So 1, 2, 3, 4, 5, 6, and so it's pairing the corresponding things. And if I give something that's the wrong length, it's better use the one we've just defined rather than the one from the library. So good idea to reload it first. Good, finally we're there. So notice I've just explicitly said that I mean the one from main but two of them work. And this is actually a hack at the REPL. It's if it doesn't know which type you're talking about and you've given the list syntax, it defaults to list because typically that's what you want. You can be explicit. You can be explicit if you need to be. Yeah.
This is a very practical question, but
good.
The only reason why Printf isn't
together because it's just such a complex program?
Yeah, so the question is the reason it didn't find a more interesting program like reversing and appending the list because that's a complex program? Yes, it is, basically, that's the reason. The implementation of this expression search really is embarrassingly simple. It's like, you know when you watch, I don't know, Penn and Teller do an amazing magic routine where they've done something that looks really spectacular, and then you learn the secret and it's really silly. And it's really disappointing almost. It's exactly like that. It really is just brute force. Does this type check? No. What about the next one? Does that type check? No. But it's that simple, but it's really surprisingly powerful. There's a lot you can do with it. We'll see examples as we go on. I just want to show what happens if you give the wrong length. So, I've given two vectors of different lengths, and it's complained. Again, it's come down to, well, it doesn't know exactly what the length is. It knows that at this point it's supposed to have found something of length 0, and it's actually found something of some successor. So it's complaining. Oh, I didn't want to go into Vim, did I? Nobody saw that. It's a muscle memory thing. It's right. So let's do. We've got 10 minutes before the break. Is that about right? This is my favourite little example of working with vectors, and something I've done with our undergraduates. So for the last few years, I've been teaching a data structures course in Java, which is actually a lot of fun. So it's basically a lot of the fundamentals of data structures in the language that they happen to know. And there comes a point later in the course where we've taught them linked lists and trees and so on, and we give them a file of tests of what their list programs have to do. So and then they have to write the program that passes that test. So one of the things we make them do, which they hate, is give them nested linked lists, so a linked list of linked lists, and then ask them to transpose it. Anyone fancy doing that in Java? No, I didn't think so. I'm glad they do it rather than me. It's a horrible thing to have to think about. So what I'm going to do is exactly that, but I'm going to use vectors rather than linked lists. I'm going to make explicit in the type that what I'm trying to do is change basically rotate this matrix, this vector of vectors. And rather than trying to figure out the details of what to do with the list, we're just going to look at the types as we go and see if the types help us get to the right program. So start, as always, with generating the candidate definition. So we've got a vector x's. We're trying to transpose it. What do you think we're going to do first? We don't really have many choices. K-split on x's, yeah? Let's do that. So what do we have to do in this first case? Transpose math RHS1. So we're trying to make m empty vectors. And we could do that now. I can't be bothered to do that now. So what I'm going to do is rename that whole. And if I hit Control-Alt-L for lifts, that will give a top-level definition, which, when I get round to implementing it, will be the program. Okay? So we'll come back to this. It's a hole we're going to need to fill, but we'll do it later. So what about in this case, the xcons x's case? So we can look at the types of things. We see that we have a k by m vector called x's. We have a vector of m things called x, and we're trying to make a vector of m vector of successor of k things. So somehow, I mean, it feels like a good thing to do at this point. We've got a two-dimensional vector here, k by m, but what we'd really like is to have an m by k thing. It feels like somehow swapping the m and k would be useful. The good news is we already have a way to do that. It's transpose. So it's what I like to tell students when they first encounter recursion is you're allowed to assume the program already works, but only for smaller things. So we're allowed to assume that transpose works, but only for x's. So this syntax here This is just defining an intermediate, like a local variable, so just giving a name to a more complex expression. So the syntax, let variable name equal expression in scope. So if we check the type now, we see we've got one more thing. X's trans is now an m by k vector. So we're in a situation where we have, well, I'll tell you what we'll do. Rather than, I've given away that I've done this before. So who'd have thought it? I actually prepare these, believe it or not. We'll just invent a name and lift it. It's as soon as you have something that's a bit hard to do, make another function to do that harder thing, and then it's just easier. So in this case, because I have done it before, I happen to know that I'm not going to need the initial vector. I'm just going to need the transposed one. So let's get rid of that. Right, so good idea to reload, see if it still type checks. So it does. So we've completed the definition of transpose mat, but we do have these two other things that these intermediate things that we haven't done yet. So let's do transpose helper next. And so I'll make this visible actually, that would help, wouldn't it? I'm used to having a slightly wider screen. So if we look at the types of these things, so look at the types of everything we have available. We have a vector of m things, we have another vector of m things, and we need to make a vector of m things, which might be seeming slightly familiar because we just did zip. So if you look at the numbers involved here as well, so x is we've got a vector of m things, that's our x, there's our m things, and we've got a vector of, what was it, m by k things, so that's like this is m here, so that's m, that's k. So what we have to do, somehow this thing, we have to rotate this thing onto here so that it's rotated like that, yeah? That, you sort of visualize what it is we're trying to achieve here? So we've got the transposed thing, it's just this vector that we're trying to rotate onto it. So once you've visualized what you're trying to do here, we can look at the program and see, okay, how are we going to write this program? So X's trans is m by k. We're trying to make m by successor of k. So somehow if we take the corresponding elements of x and x's trans and put, for each of the elements of x, we put them on the corresponding vector in x's trans, that will give us what we're trying to do, which actually is pretty much exactly what we did with zip. So what I'm going to do, I'm not even going to think here. I'm going to k-split, search, k-split, search, check if type checks. Brilliant, we've done it. Now do that in Java for 10 credits with linked lists. No, don't do that. So there's one more thing we have to do before we run this. In fact, actually, that was a question earlier. What happens if you try to compile and run something with holes? So I just happen to have made a main program for this, where what you do is enter the dimensions for a vector, it invents a vector, and then prints the transposed version. Notice there's a hole, main.empties. So I'll try compiling and running it anyway. It says, warning, if you evaluate any of these, it will crash at runtime. And it says abort. So this is the one. This is the vector it's invented, and it says abort. Attempt to evaluate whole main.empties. So you can run these things. If you do try to run them, it will tell you where it went wrong. So it's like if you're used to Haskell and you've got an incomplete program, you maybe put a typed hole in, or undefined if you're using an earlier version of Haskell. It's kind of like that. You can still have undefined things, but we give explicit holes so you can see where the problem has come from. You can see what you need to fill in. So let's just, done it again. So let's go back to empties. So just to complete, making a vector of m empty vectors is just going to be recursively on m. So we have a slightly irritating problem here, which is that m isn't an argument to this, or it isn't an explicit argument to this. So how are we going to do it? What we can do, so just like before where I showed you with append and you can explicitly say what the length is, we can actually bring m into scope. So even though it's an implicit argument, but it is a real argument. Even though it's there implicitly, it is a real thing. So we can do all the usual stuff on it. So I'll do k-split on m. This is the syntax for saying what m could. There's too many brackets there. We don't need those brackets. And again, we can do a search, and that will give us our vector of empty vectors. So let's run it again, just to show you that it really does compile and run. So let's have a. Actually, maybe I should do something where the sizes are more obviously different. So there you go. It's invented a vector and then it's transposed it, so you can hopefully believe that this is the program I've just written and it works. So one more thing to finish off. You don't have to use the REPL. So there are ways of compiling executables and maybe something that you can distribute. So I could do something like -o. And actually what I think I'll do, I talked about code generation and in different backends. So what I'm going to do is this one. Am I in the right directory? So your basic enterprise-ready PHP. So you're laughing as if you've seen a PHP program before. Right, so next time you need to write a WordPress plugin, I suggest you do it in Idris. I guess that's a good time to stop. So and leave. Okay, I'll. More on this. We'll talk more about proofs tomorrow, I think. We'll do a bit of equality proofs and predicates. And but if you do have any questions, your bits of paper, if you plonk them down here, and I will try to. If anyone has written something on a really massive piece of paper to increase their chances, then I think I'll disqualify them. I think that's my way of making it fair. So, okay, thank you.